Module 3, Lecture A, Functions for Medicine. By the end of this lecture, you will be able to define Python functions that calculate common medical values from supplied measurements, use parameters, return values, and docstrings to make clinical calculation code reusable and understandable, and test functions with realistic example cases and expected medical outputs. Reusable medical formulas, BMI functions. BMI, or body mass index, is a simple measure based on height and weight, commonly used in health screening and education. Writing the BMI calculation as a Python function makes it reusable for checkups, studies, or other workflows. This keeps the calculation separate, clear, and consistent across applications. A BMI function should clearly state what units it expects for height and weight, because mixing systems like kilograms and meters with pounds and inches can produce misleading results. Its name and inputs should make those assumptions clear so the calculation is interpreted consistently. Reusing the same well-defined function helps keep BMI results reliable and clinically meaningful. BMI functions in clinical programming show that even simple calculations require careful design. The function should produce accurate, clear results without treating BMI as a diagnosis, since it must be interpreted alongside factors such as age, sex, and medical history. In educational software, realistic test cases with different heights and weights help demonstrate the importance of precise definitions and clear assumptions about input measurements. Python code, BMI functions. BMI functions show how clinical calculations can be made reusable. Clear parameters specify the expected medical measurement units, while return values make the results easier to test and use again. The BMI metric function calculates body mass index from weight in kilograms and height in meters. It first checks that both values are positive, raising an error if either is 0 or negative. It then divides the weight by the height squared and returns the result rounded to 1 decimal place. The code computes body mass index by dividing weight in kilograms by height in meters squared. It then rounds the result to 1 decimal place, making the BMI value concise, consistent, and easy to read. This function calculates body mass index using pounds for weight and inches for height. Before calculating, it checks that both values are positive. If either value is 0 or negative, it raises an error to prevent an invalid BMI result. The code calculates body mass index using imperial units by adjusting weight in pounds and height in inches with the standard conversion factor. It then divides by the squared height and rounds the result to 1 decimal place for a clear standardized BMI value. The BMI category function classifies an adult BMI value. If the BMI is below 18.5, it returns underweight, meaning the value is below the healthy range. The function categorizes BMI using 2 cutoff points. A BMI below 25 is labeled as a healthy range, while a BMI below 30 is labeled as an overweight range. Together, these checks place adult BMI values into standard health categories. If a BMI value is 30 or higher, the function classifies it as being in the obesity range. This is one condition in a set of BMI checks that assign each value to the correct health category. The BMI calculations are tested with 3 examples across 2 measurement systems. 2 cases use metric units, with weights and heights in kilograms and meters, and 1 case uses imperial units, with weight in pounds and height in inches. Together, these examples check that the BMI functions work correctly for both metric and imperial inputs. The output shows BMI values and categories for 3 adults, using metric units for adults A and B and imperial units for adult C. It also gives an expected value for adult A of about 22.9 as a comparison point. Overall, the example demonstrates that the BMI functions reuse one formula safely and consistently across unit systems. This script calculates body mass index for both metric and imperial measurements. It checks that weight and height are positive, computes BMI with the appropriate unit conversion, and rounds the result to 1 decimal place. It also classifies each BMI as underweight, healthy, overweight, or obesity. Sample tests print the calculated values and categories to show that the functions work consistently across unit systems. Medication dose calculations. Reusable functions make medication dose calculations more consistent and efficient by using inputs such as weight, age, and kidney function to produce a dose. In Python, placing this logic in functions reduces repeated manual work and makes the calculation easier to read and check. These functions support but do not replace clinical judgment because safe dosing still depends on accurate inputs and clear assumptions. When designing a medication dose calculation function, first define the exact inputs it needs and the result it should produce. Keep the function focused on one clinical task, such as finding a daily dose or converting an ordered amount into a volume. Because medication calculations often involve different units, clear and predictable inputs and outputs help prevent confusion and reduce the risk of errors. Functions can make medication dose calculations safer and more consistent, but they must be designed with clear limits and used with clinical judgment. Pediatric doses, maximum dose checks, tablet strengths, and liquid concentrations all affect whether a calculated result is appropriate. Treating these calculations as functions helps learners build precise, reviewable, and context-aware clinical programming habits. Python code medication dose calculations. Functions help make medication calculations reusable, while clear parameters reduce the risk of mixing up units. Even when examples produce results, those outputs must still be reviewed clinically. A dose calculation function uses a patient's weight in kilograms and the prescribed milligrams per kilogram to determine a daily medication dose. Before calculating, it checks that both inputs are positive. If either value is 0 or negative, it raises an error to prevent unsafe or inaccurate dosing. The calculation finds the total daily medication dose by multiplying the patient's weight in kilograms by the recommended dose per kilogram. This helps adjust the dose to the patient's body weight for accurate clinical dosing. This function determines the medication amount for each scheduled dose, using the total daily dose and the number of doses per day. It checks that both values are positive and raises an error if either is 0 or negative. This validation helps prevent unsafe or inaccurate dosage calculations. This calculation finds the milligrams of medication for each dose by dividing the total daily amount by the number of doses per day. It helps make each scheduled dose consistent and evenly distributed. This function determines the liquid volume needed for a medication dose using the ordered dose and the medication concentration. Before calculating, it checks that both values are positive. If either value is 0 or negative, it raises an error to prevent unsafe or invalid dosage calculations. This calculation finds how many milliliters of liquid medication are needed for the prescribed dose. It divides the ordered dose in milligrams by the medication concentration in milligrams per milliliter, giving the correct volume to administer. This example calculates a pediatric liquid medication dose for an 18-kilogram patient. The recommended daily dose is 40 milligrams per kilogram, divided into 2 scheduled doses per day. The medication concentration is found from 250 milligrams in 5 milliliters, which equals 50 milligrams per milliliter, and is used to determine the volume needed for each dose. To find the total daily medication dose, use the daily weight-based dose function with the patient's weight in kilograms and the recommended milligrams per kilogram per day. It multiplies these values to determine the full amount needed for one day, helping ensure the dose matches the patient's weight. To calculate each medication dose, divide the total daily dose by the number of doses taken per day. This gives the milligrams needed for one dose and helps distribute the medication evenly to maintain consistent therapeutic levels. To find the liquid volume for a dose, use the liquid volume function with the ordered medication amount in milligrams and the medication concentration in milligrams per milliliter. It returns the required volume in milliliters, helping ensure the dose is measured accurately for administration. This example prints a concise medication dose summary, including the patient's weight, the total daily dose, each individual dose, and the liquid volume needed per dose with appropriate rounding. It ends by reminding the user to verify dose limits, rounding decisions, and patient-specific factors to ensure the result is clinically appropriate. This script estimates medication dosing from a patient's weight. It calculates the total daily dose, divides it into the prescribed number of daily doses, and converts each dose into a liquid volume using the medication concentration. The output reports the weight, daily dose, dose amount, and volume per dose, but the results must be checked against clinical guidelines. Dose calculations. Dose calculations turn patient information such as weight, age, or body surface area into clinically meaningful medication doses. Python functions can encode these rules, such as weight-based pediatric dosing, body surface area dosing in oncology, or weight and time-based infusion rates in critical care. This helps learners see how clinical dosing logic becomes reusable computational tools rather than manual calculations. When designing a dose calculation function, first define the required measurements and keep units consistent. The function should make clear whether it calculates a total daily dose, a single administration dose, or a conversion between the two, because a correct number can still be unsafe if its meaning is unclear. Focusing each function on one clinical task helps learners understand the needed inputs, the expected output, and how to use the result safely. Dose calculation functions show how basic arithmetic becomes reliable clinical software. Because these calculations may be repeated across patients and medications, functions help keep the computational steps consistent and accurate. They do not replace clinical judgment or policy, but they can standardize how doses are calculated. Learners should name these functions clearly and make their purpose specific, so the measurements and dose types are easy to understand. Python code. Dose calculations. Functions make repeated medication calculations clearer and more consistent. Their parameters represent the measurements used in the formulas, and their returned values help support safe checking. The single dose milligrams function calculates a medication dose from a patient's weight and the dose rate, while respecting a maximum limit. Before calculating, it checks that both values are positive. If either value is 0 or negative, it raises an error to prevent invalid dosing calculations. The code calculates a weight-based medication dose, limits it so it does not exceed the maximum allowed amount, and rounds the result to 1 decimal place. This helps provide a precise dose while supporting safe medication administration. The daily dose milligrams function calculates a patient's total daily medication dose using body weight and a dose rate in milligrams per kilogram per day. Before calculating, it checks that both values are positive. If either value is 0 or negative, it raises an error to prevent invalid clinical inputs from being used. The code finds the total daily medication dose by multiplying the patient's weight in kilograms by the daily dose rate per kilogram. It then rounds the result to 1 decimal place for clear and precise dosage instructions. The dose each time function calculates the amount of medication for each dose by dividing the total daily dose by the number of doses per day. Before calculating, it checks that both inputs are positive. If either value is 0 or negative, it raises an error to prevent invalid or unrealistic dosing results. The code finds the dose for each administration by dividing the total daily dose by the number of doses per day. This helps spread the medication evenly across the day, and the result is rounded to 1 decimal place for consistent dosing. The example sets 2 body weights for medication dose calculations, 18 kilograms for a child and 72 kilograms for an adult. These realistic reference values are used to show how dosing functions adjust results based on body weight. A child's antibiotic dose is calculated using the single dose milligrams function with the child's weight, the dose rate, and a maximum allowed dose. For an 18-kilogram child and 15 milligrams per kilogram, the function computes the weight-based dose and caps it if needed at 500 milligrams. The calculated single dose is then printed in milligrams. The adult's total daily dose is calculated from body weight using a dose rate of 20 milligrams per kilogram per day. The result is stored and then displayed in milligrams per day for clarity. Calculate the dose for each administration by dividing the adult total daily dose by the number of doses taken per day. In this case, the daily dose is split into 3 equal parts. The result is then shown in milligrams, helping confirm that the medication is evenly distributed throughout the day. The code performs basic validation checks for dose calculations. It confirms that the child's single dose equals 270 milligrams, and that the adult dose per administration equals 480 milligrams. These tests help ensure the calculation functions return the expected results. This script calculates medication doses from a patient's weight and dosing rules. It includes separate calculations for a single dose, a total daily dose, and dividing that daily amount into multiple administrations. In the examples, an 18-kilogram child receives a capped antibiotic dose of 270 milligrams, while a 72-kilogram adult receives 1,440 milligrams per day, split into 3 doses of 480 milligrams. Simple tests confirm that these results match the expected values. Reusable function design. Clear parameters. Reusable clinical functions need clear parameters so users know exactly what information to provide. In healthcare, this is essential for accuracy and patient safety, especially for inputs such as weight, height, or serum creatinine. Each parameter should be labeled clearly with its units, such as weight in kilograms, to prevent confusion in clinical or research use. Clear, well-named parameters make clinical software easier and safer for different users to share and understand. When parameter names match real clinical measurements, such as units, timing, or patient characteristics, users can see what information a calculation needs and avoid confusion. This is especially important in dosing, where distinctions like total body weight versus ideal body weight can affect results. Clear parameters do not replace clinical judgment, but they make calculations more transparent and reduce the chance of mistakes. When designing reusable function parameters, focus on what future users truly need. Include only inputs that affect the result, and avoid hidden assumptions or unnecessary complexity. Use consistent parameter names across functions to reduce mistakes, especially with units, and to make the functions easier to test, understand, and trust. Python code, clear parameters. Clear function parameters help prevent mistakes in clinical calculations, especially when names include the measurement units. Return values also make functions easier to reuse in different parts of a program. The calculate BMI function computes body mass index from a person's weight in kilograms and height in centimeters. It returns the BMI value so the same function can be reused with different inputs. Its name and description make its purpose clear to users. The code changes height from centimeters to meters by dividing by 100, because body mass index must use height in meters to calculate correctly. The code first checks that the height is greater than 0. If not, it raises a value error to show the height must be positive. This validation prevents invalid input from causing mistakes in the body mass index calculation. The function calculates body mass index by dividing weight in kilograms by height in meters squared. It rounds the result to 1 decimal place for consistent, reusable output. The calculate infusion rate function determines how quickly fluid should be given in milliliters per hour. It uses the total volume in milliliters and the infusion time in hours to return a clear, reusable rate for clinical calculations. The code verifies that the time value is positive before continuing. If the time is 0 or negative, it raises a value error, preventing invalid input from causing incorrect calculations. The function calculates the infusion rate by dividing the total volume in milliliters by the time in hours. It returns the rate in milliliters per hour, rounded to 1 decimal place for consistent, precise reporting. This test checks the calculate BMI function using realistic patient measurements. It uses a weight of 70 kilograms and a height of 175 centimeters to simulate a typical BMI calculation. This test checks the infusion rate calculation using 500 milliliters over 4 hours. The function divides the volume by the time to find the rate in milliliters per hour, and the result is stored for later use or display. This line displays the calculated body mass index in the console. It uses the print function to show a clear label, the stored BMI value, and the units, kilograms per square meter, making the result easy to read. The code displays the calculated infusion rate in milliliters per hour. It labels the result clearly as the infusion rate, followed by the numeric value and unit, so the output is easy to understand in a clinical setting. The message emphasizes that function parameters should have clear, meaningful names. Including units and parameter names helps show what the function expects before calculations begin, which improves readability and helps prevent mistakes. The script calculates 2 clinical metrics, body mass index and infusion rate. It uses descriptive parameter names with measurement units to make the code clearer and less error-prone, and it checks for invalid values such as non-positive height or time. In the example, it reports a body mass index of 22.9 and an infusion rate of 125 milliliters per hour. Return values. A return value is the result a function gives back after it finishes. allowing that result to be reused elsewhere in a program. In medical programming, a function may use inputs such as height or temperature, but it should return the calculated result rather than only display it. For example, a body mass index function should return the index so the program can compare or categorize it, which keeps the function focused and easier to test. Good return values make clinical calculation code safer and easier to understand by matching the calculation's purpose and the user's needs. A function may return one result, such as an estimated dose, or several related results, such as a score and its interpretation. Keeping return types consistent makes outputs predictable, reduces errors, and helps programmers follow the path from raw data to clinical result. Functions used with clinical examples should return results, not just display them, so their outputs can be checked against expected values. This makes it easier to catch errors, support documentation, and trust the calculations during revisions. In clinical applications, where small mistakes can matter, clear return values help make functions reliable parts of larger tools such as medication screening or health record summaries. Python code return values. Return values make calculations reusable and easier to test. Clinical functions should return results instead of printing them invisibly, so tests can compare those results reliably. The calculate BMI function computes body mass index from weight in kilograms and height in meters. It first checks that both values are greater than 0 and returns none if the input is invalid. Otherwise, it calculates BMI as weight divided by height squared and returns the result for reuse with different inputs. Before calculating body mass index, the code checks that both weight and height are greater than 0. This prevents invalid calculations, such as dividing by 0 or using non-positive values. If either input is invalid, the function returns none instead of continuing. This code calculates body mass index by dividing weight in kilograms by height in meters squared. The result helps indicate whether a person is underweight, healthy, or overweight, and the function returns it for later use or analysis. The inches to meters function converts a height from inches into meters. It does this by multiplying the inch value by 0.0254, then returns the converted height. The code converts height from inches to meters by multiplying the inch value by 0.0254. It then returns the converted height so it can be used wherever a meter value is needed. The interpret BMI function assigns a simple category to a BMI value. If the value is missing, it returns invalid measurements. Otherwise, it labels BMI values below 18.5 as underweight, values below 25 as healthy range, and all higher values as above healthy range. This part checks whether the BMI calculation is valid. If the result is missing because the input was invalid or the calculation failed, the function returns a clear message saying the measurements are invalid. The code classifies a BMI value below 18.5 as underweight. In that case, the function returns the underweight category using the standard BMI cutoff. The code checks whether a BMI value is below 25. If so, it labels the result as a healthy range, meaning the BMI falls within the standard normal range for adults. This part of the function labels a BMI value as above the healthy range when it does not fit earlier categories, such as underweight or healthy range. It provides a clear category for BMI values that are higher than the healthy range. The example calculates BMI in two cases. First, it uses the BMI function with a weight of 70 kilograms and a height of 1.75 meters. Then it converts 68 inches to meters and uses that converted height to calculate BMI again for a weight of 82 kilograms. We verify the BMI functions by comparing their results with expected values for both metric and imperial calculations. Each calculated BMI is rounded to 2 decimal places before checking it against the benchmark. Matching results confirm that both calculations are accurate and reliable. The code creates concise result messages for both metric and imperial BMI calculations. Each message shows the BMI rounded to 2 decimal places and includes an interpretation from the BMI interpretation function. It also summarizes whether the metric and imperial BMI tests passed based on earlier comparison results. The output summarizes BMI results in both metric and imperial units, including each interpretation. The imperial result shows that the calculation still works after converting height from inches to meters. A final test line checks the results against expected clinical examples to confirm the calculations are accurate. This script calculates and interprets body mass index using metric and imperial inputs. It computes BMI from weight and height, converts inches to meters when needed, and labels the result by health range. When run, it tests 2 examples. 70 kilograms at 1.75 meters gives a BMI of 22.86 in the healthy range, while 82 kilograms at 68 inches gives 27.48 above the healthy range. It also reports whether the results match with expected test values. Docstrings for clarity. Docstrings are essential in clinical calculation functions because they explain what the function does and how to use it safely. They should state the clinical value being calculated, the expected measurements in units, and the type of result returned. This helps prevent misleading results from incorrect assumptions and gives future users a reliable reference when reading or reusing the code. Medical docstrings should explain the clinical purpose, required inputs, units, assumptions, and exact output, rather than just restating the function name. For example, a body mass index calculation should say it uses adult height and weight in specific units and returns a number, not a diagnosis. Dose calculations should clarify whether the result is a daily total or a single dose. Clear boundaries make clinical code easier to review, test, and use safely. Docstrings make functions easier to understand, verify, and reuse. They clearly explain a function's purpose, inputs, and outputs, so others can integrate it without having to decipher the logic. In clinical or professional software, this supports safer, more maintainable tools by preserving meaning and reducing ambiguity. Python code, docstrings for clarity. Docstrings should clearly explain what clinical functions do, carefully document any units, and describe return values in plain language. The calculate BMI function computes an adult body mass index using weight in kilograms and height in meters. Its docstring explains that the result is a numeric index, not a medical diagnosis, and clearly states the required units. This helps users provide consistent inputs and use the function correctly. The parameters section of a docstring explains what inputs a function expects. Here it states that body weight should be given in kilograms and standing height in meters, helping users provide the right values for the calculation. The function calculates body mass index as a numeric result, but it does not provide a medical diagnosis. Before calculating, it checks that both weight and height are positive. If either value is 0 or negative, it raises an error instead of continuing. The code computes body mass index by dividing weight in kilograms by height in meters squared. It then rounds the BMI to one decimal place, making the result simple and easy to interpret. The calculate daily dose function determines a patient's total daily medication dose from their weight and the ordered dose per kilogram. Its docstring briefly explains the function's purpose, identifies the two required inputs, and states that the result is the total daily dose in milligrams. This makes the function's use and expected output clear to anyone reading it. The parameters section of the function description explains the inputs needed to calculate a medication dose. It includes the patient's weight in kilograms and the prescribed daily dose per kilogram. Together, these values allow the dose to be adjusted accurately to the patient's body weight. The function calculates the total daily dose in milligrams, but first confirms that both the patient's weight and the dose per kilogram per day are positive. If either value is 0 or negative, it raises an error to prevent invalid input from being used. The code finds the total daily medication dose by multiplying the patient's weight in kilograms by the prescribed amount per kilogram per day. It then rounds the result to one decimal place for a clear, precise dosage. The example shows two practical health calculations using functions. One function calculates a patient's body mass index from weight and height, and another calculates a total daily medication dose from body weight and the prescribed milligrams per kilogram per day. Together, they demonstrate how functions can return useful patient-specific results. The output shows the calculated BMI with its units, then an expected BMI value for comparison. It also prints the calculated daily medication dose and a reference dose to help verify accuracy. Finally, it displays the first line of the BMI calculation function's docstring, demonstrating how concise documentation can be accessed and used. The script defines documented functions to calculate body mass index and a weight-based medication dose. It then tests them with example values, producing a BMI of 22.9 and a daily dose of 270 milligrams. The output compares these results with expected values and also shows how to access the first line of a function's documentation. Testing clinical functions. Example test cases. Clinical calculation tests should use realistic patient scenarios to confirm that results match clinical expectations. Inputs such as height, weight, and medication dose should reflect plausible adult or pediatric cases rather than arbitrary numbers. Each test case should combine patient data with the calculation and verify that the outcome is appropriate for real-world use. Test cases should cover both common clinical scenarios and values near important decision thresholds. Typical cases show that a function handles routine calculations, while boundary cases reveal whether it responds correctly when interpretations or doses may change. Relying only on average values can create false confidence, so testing near key clinical cutoffs makes results more reliable and relevant. Realistic test cases make clinical calculation code safer and easier to review. Using familiar clinical inputs helps reviewers judge whether a calculation matches expected practice. But the units and context must be correct to avoid misleading results. In health programming, tests should reflect real clinical situations, so both the math and its assumptions are valid. Python code. Example test cases. Clinical functions should be tested with realistic cases, clear expected outputs, and boundary cases that can expose calculation errors. The method calculates adult body mass index using a person's weight in kilograms and height in meters. It finds BMI by dividing weight by height squared, then uses the result to classify the person as underweight, normal weight, overweight, or obese. The code classifies a person's BMI using standard health ranges. A BMI below 18.5 is labeled underweight, while a BMI below 25 is labeled normal if it is not already underweight. This code assigns a BMI category based on the calculated value. A BMI below 30 is classified as overweight, while values that do not match earlier conditions are classified as obesity. This ensures each BMI falls into a defined category for identifying related health risks. This line returns the body mass index rounded to 1 decimal place along with its weight status category. The rounded value makes the result easy to read and compare, while the category gives a quick clinical interpretation such as underweight, normal, overweight, or obesity. The pediatric dose function calculates a child's medication dose using the child's weight in kilograms and the prescribed milligrams per kilogram. It multiplies these values to get the total dose in milligrams, rounds the result to 1 decimal place, and returns the rounded dose. A set of test cases is created to check the clinical functions. Each case includes a descriptive name, the actual result from calling a function with chosen inputs, and the expected result. For example, the BMI category function can be tested with a specific weight and height, then compared with the expected BMI value and category. This structure makes it easy to verify that the functions return correct outputs. This test case checks a pediatric medication dose calculation. It uses a weight of 18 kilograms and a dosage of 10 milligrams per kilogram, so the expected dose is 180 milligrams. The case helps verify that the dose calculation function returns the correct result. The test results are collected in a summary list. Each test case compares the function's actual output with the expected output, then marks it as passing if they match or needing review if they do not. The stored summary records the test name, both results, and the comparison outcome. The code prints a header for the clinical function tests, then reviews each test case in the summary. For each one, it shows the case name, the actual and expected results, and whether the test passed or needs further checking. This gives a quick overview of which tests succeeded and which may need investigation. The code counts how many test cases passed by checking each result in the summary and totaling those marked as passing. It then prints the number of successful tests alongside the total, giving a quick overview of the test results. This script quickly checks 2 clinical calculations, body mass index classification and pediatric medication dosing by weight. It runs predefined cases including a typical adult, a BMI boundary case, and a specific pediatric dose scenario. Each result is compared with the expected answer and labeled as passing or needing review. The script then prints a summary and counts how many tests passed, giving a basic validation of the functions in realistic situations. Expected outputs. When building clinical functions, define the expected outputs before testing the code. These outputs connect technical results to clinical meaning, such as matching body mass index calculations to trusted sources, or applying correct medication dosing rules and units. This helps separate sound clinical logic from correct programming implementation, reducing the chance of accepting wrong results just because the program runs. It also encourages safer programming habits. Expected outputs for clinical functions should be realistic, precise, and tied to the clinical context. Tests should cover relevant ranges such as normal, fever, and hypothermic temperatures, and consider different patient groups such as adults and children when errors have different clinical impact. They should also verify appropriate rounding and ensure results are not only accurate, but clear and safe for clinical use. Expected outputs should be verified independently, not accepted just because a function produces them. Use manual calculations, validated examples, or trusted tools to confirm the results, especially when incorrect assumptions or unit conversions could make a function consistently wrong. Writing expected outputs in plain language also clarifies the function's purpose and supports safer programming practices, particularly in clinical contexts. Python code. Expected outputs. Expected outputs help make clinical function tests safer and more reliable. Using small examples simplifies checking calculations, while independent values reduce the risk of trusting faulty code. The BMI calculation function takes weight in kilograms and height in meters, and first checks that both values are positive. If either value is 0 or negative, it raises an error, because those inputs are not valid for this measurement. When the inputs are valid, it calculates BMI as weight divided by height squared, then returns the result rounded to 1 decimal place. The code calculates body mass index by dividing weight in kilograms by height in meters squared. It then rounds the result to 1 decimal place, making the BMI easier to read and compare. This function converts a Celsius temperature to Fahrenheit by applying the standard scale conversion. Multiply by 9/5, then add 32. It returns the result rounded to 1 decimal place, giving a concise value for practical use. A set of test cases is created to check 2 clinical calculation functions. One case verifies that the body mass index calculation for a 70-kilogram adult who is 1.75 meters tall returns 22.9. Another checks that converting 39 degrees Celsius gives 102.2 degrees Fahrenheit. Together, these tests help confirm that the clinical calculations produce reliable, expected results. The code runs through each test case, takes out the case name, the function, its inputs, and the expected result, then calls the function with those inputs. It compares the actual result to the expected one to decide whether the test passed. Finally, it prints a clear summary showing the test name, expected result, actual result, and pass status, helping confirm that each function behaves correctly. The code prints a message emphasizing that expected outputs are essential in testing. They help confirm that both the clinical logic and the implementation work correctly, supporting reliable results in settings where accuracy is critical. The script defines functions to calculate body mass index and convert Celsius to Fahrenheit, then checks them with known test cases. It compares each function's result with the expected value and reports whether the test passed. This shows how expected outputs help verify that clinical calculations and their implementations are working correctly. Unexpected clinical inputs. Clinical software should be tested with unexpected inputs because real-world data can be missing, unusual, or entered in the wrong units. Tests should check whether calculations handle values like 0 or negative height, extreme or missing weight, and pediatric cases safely. This helps distinguish rare but possible clinical values from likely data entry errors or unit mismatches. When testing unexpected inputs, check both the calculation and whether the result makes clinical sense. A function may return a precise number from invalid data, such as an impossible age or the wrong unit, but that output can still be misleading or unsafe. Tests should confirm that out-of-bounds inputs are detected, problems are explained clearly, and invalid results are not presented as trustworthy. Healthcare programming tests should include realistic edge cases that reflect clinical uncertainty, such as missing data, pending results, outdated measurements, and special patient populations. The goal is not to make simple educational functions handle every medical decision, but to teach students to question inputs before trusting outputs. Reliable medical software depends on accurate calculations, good data quality, patient context, and clear communication of uncertainty. Python code, unexpected clinical inputs. Clinical functions should be tested with unexpected inputs to make sure they behave safely. In this example, BMI input cases are checked to confirm the expected clinical response. The calculate BMI function takes weight in kilograms and height in meters, then validates the inputs before computing a result. It rejects missing, non-positive, or implausible values, including heights or weights outside broad human ranges that may indicate wrong units. If the inputs are valid, it calculates body mass index as weight divided by height squared and returns the value rounded to 1 decimal place. The code checks whether the weight or height is missing before doing any calculation. If either value is absent, it returns an invalid input message right away. This prevents errors and avoids producing unreliable results from incomplete data. The code first checks whether the weight or height is 0 or negative. If either value is invalid, it returns a message saying the measurement is not valid. This prevents the function from using impossible or incorrectly entered data. The code checks whether a height in meters falls within a realistic human range. If the value is below 0.4 meters or above 2.7 meters, it returns a warning that the input may use the wrong units. The code validates a person's weight by checking whether it falls within broad human limits. Values below half a kilogram or above 700 kilograms are treated as invalid, and the code returns a message that the weight is outside the allowed range. This helps catch unrealistic or incorrect input before it causes errors. Body mass index is calculated by dividing weight in kilograms by height in meters squared. The result is then rounded to 1 decimal place to make it easier to read and compare consistently. The test cases cover several scenarios for checking a BMI calculation function. They include a typical adult with an expected BMI of 22.9, a 0 height that should be invalid, a height entered in centimeters instead of meters that should also be invalid, a small neonate with an expected BMI of 12.8, and a missing weight value that should be invalid. Together, these cases test both normal inputs and common error conditions. The code introduces the results of unexpected input tests for the BMI function. It briefly explains what the upcoming output represents, helping learners understand the purpose of the test cases being shown. The test first checks whether the expected result is marked invalid. If so, it passes when the actual result is a string that begins with the word invalid. Otherwise, it simply compares the actual result with the expected value to decide whether the test passes. The code prints one short summary line for each test case. It labels the result as pass if the test succeeded, or check if it needs review, then includes the test label and BMI calculation result. This gives a quick overview of whether each case behaved as expected. The code ends by printing a reassuring console message. It emphasizes that the function handles unexpected input safely, helping prevent misleading clinical results and supporting reliability in clinical use. This script tests a body mass index calculation function to make sure it handles invalid clinical inputs safely. The function rejects missing, non-positive, or implausible height and weight values, and only calculates a rounded BMI when the inputs are valid. The tests cover normal and edge cases, then report whether each result matches the expected outcome. Overall, the goal is to prevent misleading clinical results from bad input data. In this lecture, you learn to define Python functions that calculate common medical values from supplied measurements, use parameters, return values, and docstrings to make clinical calculation code reusable and understandable, and test functions with realistic example cases and expected medical outputs. In the next lecture, Lecture B, we will go over rules and validation. Thank you for your attention. See you all in the next lecture.